In this screencast, I'm going to give you the idea behind the proof of the Bolzano Weierstrass theorem, which basically says if you have a bounded sequence, then it has to have a convergent subsequence. And the idea behind this proof is really cool, I think. So what we have, let's draw a number line. This sequence is bounded, so what that tells us is that there's a capital M. Let's draw in a 0. There's a capital M somewhere. It's positive. And how about a negative M? Where what we know is that we know that all of the a sub n have to be in this range. Well, that's great. That doesn't help us get a convergent subsequence yet. But what we can do is we can say, okay, there are an infinite number of these guys. So let's split this up into two different parts. We have a blue chunk, and we have, how about, let's go with a red chunk. I'm going color happy here because I can. Well, there are four possibilities. Either there are only a finite number of sequence terms in the left half and only a finite number in the left, infinite in the left, finite in the right, finite in the left, infinite in the right, or they both contain an infinite number of these terms of the sequence. We don't know which one it is. But I do know that you can't have a finite number of terms in the left and a finite number of terms in the right. If you could, you just add your finite number of terms here, plus your finite number of terms here. Finite plus finite equals finite. That would tell us that there are only finite number of terms in this total thing here. Well, that's impossible since we know that it's a sequence. So a sequence have an infinite number of things. Their domain is natural numbers. So one of these two parts has to be infinite. Let's assume it's the left part. If it's the left part, then what I want to do is I want to repeat the process. I want to go take my number line, and I'm going to see what happens between negative m and 0. Once again, what I'm going to do is I'm going to split this into two different sections. I'm going to split right down the middle, negative m over 2, and then I have a left half here, call it the green half, and then maybe I'll have another red half on the right. Once again, I've split in half. On this half, there's either finite or infinite, similarly over here, but they can't both be finite. So if they're both finite, we have a contradiction, so one of them has to be infinite. Maybe this time it's going to be the right half. Well, then I get another number line that goes from, I'm only going to consider negative m over 2 to 0. If they're both infinite, it doesn't matter, just pick one. Pick whichever one you like. But we can always take half of what we have, and then we can pick half such that they're an infinite number of terms of the sequence. Well, then what happens? We have I sub naught is going to be the interval negative m to m. This is from the bound. We know it's bounded. And, right, I sub n, this gives us a sequence of things where basically I sub n, the length of it, is equal to, this has length 2m, m, and m, has 2m over 2 at the end, because it gets half as big each time. In particular, that length goes to 0. So we can always pick these intervals that contain an infinite number of things, and the intervals are getting smaller and smaller and smaller, which means we're getting an infinite number of terms that are crammed into a smaller and smaller part. Which means, now, if we take the nested interval property, this is not empty. So we're going to have these very, very small intervals, right? N's going to be huge, and that makes this thing a really tiny interval with an infinite number of terms, and the intersection is non-empty. So what that says is that we have an infinite number of these things really close to basically whatever's in this intersection, which gives us the convergent subsequence. Whatever ends up being in these small little intervals is our convergent subsequence. I don't know what the indices are. I don't know if A1's in there or not, but I know that one's there. So it's cool. You're just kind of narrowing down where they are, and you know that they're an infinite number of terms. I love this proof.